So last time we had this energy balance equation for a reacting system. So you could have a control volume, you could have some heat transfer into the control volume, you could have shaft power out of the control volume. This term right here is called the standard enthalpy of combustion. It's defined as only needing to know the enthalpy of formations of each of those products, as well as the enthalpy of formation of each of those reactants, plus the stoichiometric coefficient in the balanced reaction equation. That's what that N is. If you have the products going out hot or cold, then the difference in the enthalpy between the outgoing product temperature and the reference temperature at 298 must be taken into account. So this delta H is H bar at the exit temperature minus H bar at the reference 298 Kelvin. If it goes out at 25 degrees C, delta H's are all zero. Likewise, for each of the reactants, you have a difference in the enthalpy for the temperature it comes in at minus the reference temperature 298 Kelvin. So if it comes in at 25 degrees C, all those delta H's are zero, the summation is zero. That equation look good? Calculate the standard enthalpy of combustion for liquid octane, that's our fuel, and the answer is already given right here, negative 5,074,630. So how are we going to calculate that term? How about if I give you a second and work on that? And so what you have to do is you have to get a balanced stoichiometric equation first for the combustion of liquid octane. So let's start off with CH18. And you can emphasize that it's liquid, but in the reaction equation it really doesn't matter. But you just emphasize that it could be gaseous. Here it's liquid. All right. We're going to get the oxygen from somewhere. It's going to come from air. You're going to produce CO2. That's our desired product. How many CO2s are we going to have? 8. And then you're going to produce H2O. The only place you get the hydrogen is from the fuel. There's 18 H's. So how many H2Os? 9. We do our counting. This is 16. This is 9. 16 and 9 is 25. Hence, we now can tell for stoichiometric combustion or 100% theoretical air, we need 25 over 2. Then we're going to have no leftover oxygen, but we'll have 25 over 2 times 3.76 N2s. If you wanted to, you could replace the 25 over 2 by 12.5, right? And if you have a calculator, run 12.5 times 3.76 for me. What do you get? 47? It's a nice number, 47.0. So now that we have it balanced, we go to our equation for the standard enthalpy of combustion. The sum of the products. Now, I'm just going to start expanding that summation. So we have N times the enthalpy of formation for the, let me put the parenthesis over here, for the carbon dioxide plus the stoichiometric coefficient enthalpy of formation for the H2O plus N times the enthalpy of formation for the N2 minus N times the enthalpy of formation for what? What is the minus for? Now we're doing the reactants, not the products. The sum over the reactants. What's the first reactant that a student might forget on an exam? They'll leave the fuel out. So we want to have the CH18, don't forget that, minus N times enthalpy formation of the O2 minus N times enthalpy formation of the N2, right? Now, some of you are saying, I know some of those terms are zero. So I'm going to pause, and I want you to tell me which of those terms are 0. Got it? I'm going to pause and walk around. All right, so it's good to know that the enthalpy of formation of the nitrogen, whether it's a product or a reactant, is 0, and the enthalpy of formation of the oxygen is 0. So if you get good at this, you won't even include them in the equation. You're just like, I know it's 0, and I want to write it down and then strike it out. But let's continue on. So we have to know the stoichiometric coefficient in front of the CO2. That's 8. Then we have to get the enthalpy of formation for the carbon dioxide, negative 393,520 kilojoules per kilomole, plus the stoichiometric coefficient in front of the water, H2O, 9, times the enthalpy of formation. Now you have a choice. There are 2 enthalpy of formations for water. Is it water vapor at 25 C or water liquid? Most times the product goes out in what form? In the gaseous or vapor form. It's more traditional, put gaseous, although I could say do it for the liquid. All right, so if you do it for the gaseous, it goes out as negative 241,820 kilojoules per kilomole. Now we're going to come over here. We have negative times the coefficient for the fuel, 1. And then the enthalpy of formation for the liquid octane, negative 249,910 kilojoules per kilomole. I think this chapter is hard because there's a lot of negative signs. You got a negative of a negative. Okay, that's now a positive, but you just have to bear with the negative signs, okay? So when you do the math, you should get negative 5,074,630 kilojoules per kilomole. All right? Now that you've calculated the standard enthalpy of formation, this was our answer from the previous page. For liquid octane, I want you now to use that value to get the lower heating value. Calculate the lower heating value for liquid octane. And notice, here's the answer already. You should be able to get this answer. It's 44,430 kilojoules per kilogram. Notice, this standard enthalpy of combustion is often, is it positive or negative? And notice the lower heating value and the higher heating value, are they reported as positive or negative? They're reported as positive. So got to watch out for a negative sign. But can you move between the two? I'm going to give you a minute to do that. All right, who wants to be brave and give me the equation to go between the standard enthalpy of combustion, HRP bar naught, which is negative, and the lower heating value? It'll work for liquid octane. It'll work for a lot of fuels. Look at the units that'll help you. It's how many kilojoules of heat that are released per kilogram of the fuel. This is how many kilojoules of heat that is released in the combustion per kilomole of what? Of the fuel, isn't it? So how am I going to jump back and forth in between? So if I put 1 over the molar mass is kilograms of fuel per kilomole of fuel. And then maybe put a minus sign just to get rid of the negative, and there you go. To get the molar mass, 4.22 kilograms per kilomole. Did it work? Good. I'm on a roll. I have questions for you today. Compute the higher heating value for liquid octane, knowing that the lower heating value you just computed is this number. And also, I'm going to let you know, you don't have to look up in the table. I know you could go get it. If you needed to use HFG for water at 25 C, there it is. The heat of vaporization for water at 25 C, there it is. And I know you needed the molar mass of octane for the last problem, but you're going to need it again for this one. Okay? So how am I going to go from the lower heating value to get the higher heating value? Well, we know that this one's larger, isn't it? What are the units on higher heating value? Kilojoules per kilogram of the fuel. What are the units on here? Kilojoules per kilogram of the fuel. I'm not going to really multiply the lower heating value by something. I'm just going to add to it. What am I going to add to it? The difference is the water vapor, how it goes out. It goes out liquid. So it's like there's more heat to be transferred instead of less heat to be transferred out of the furnace. Okay, but this isn't going to cut it by itself. It has the right units of kilojoules per kilogram, but look at the units right here. It's kilogram of what for HFG? It's a kilogram of H2O. This is fuel. This is fuel. True? So what do you think I need to do to fix that? Maybe I need to have kilogram of the water per kilogram of the fuel. That looks like the air-to-fuel ratio, but it's not the air-to-fuel ratio, it's the water-to-fuel ratio. It's the water in the products per fuel, kilomole of fuel. I know it's kilogram to kilogram, right? So how do I calculate this? Kilogram of water per kilogram of fuel. How about the number of moles of the water times the molar mass of the water divided by the number of moles of the fuel to the molar mass of the fuel? I just need to get the right number of moles to number of moles. That comes from my balanced reaction equation. So for my balanced reaction equation, for every 1 mole of fuel, how many moles of vapor were produced? 9. The molar mass of water, 18.02. Molar mass of fuel, right up here, 114.22. And then you also have the HFG. Look good? I think the units really guide you through the process. If you get stuck, chase your units. When computing the standard enthalpy of combustion, what's the symbol for that? Right, that's the symbol for it. True or false? It matters if the fuel is in the liquid state or gaseous state. True or false? And then the second one, true or false? It matters if the oxygen comes from pure oxygen or if the oxygen comes from air. True or false on both of those? I'm going to pause. I'm going to come around. All right, so what do we got? The answer for this is true. Depends if it's liquid or gaseous, right? But what about the oxygen? False. Remember, the enthalpy of formation for the oxygen is 0. All right. When computing the lower heating value for a fuel, true or false? It matters if the fuel is initially a liquid or gaseous. True or false? Instead of the enthalpy of combustion, it's the lower heating value, right? I'll give you a minute. All right, so the answer, it does matter if the fuel is liquid or gaseous, but does it really matter where the air comes from, or the oxygen comes from? No, and we just did it. All right. All right, so you have gaseous methanol. There's the makeup of methanol. It comes in at 25 C and 1 ATM. It enters a furnace operating in steady state and burns complete with 100% theoretical air. That air comes in at 25 C and 1 ATM. Now, the products of combustion exit at this elevated temperature of 900 K, 1 ATM, okay? Kinetic and potential energy effects are negligible. Determine the heat transfer to the furnace from the surroundings in units of kilojoules per kilomole of the fuel. What are we asked to solve for? What symbol or ratio are we asked to solve for? The heat transfer to the furnace in units of kilojoules per kilomole of fuel. Is that the Q dot CV divided by N dot F? Sure. And then we remember, I'm probably going to use the energy balance equation. Oh, from memory, the energy balance equation is negative W dot CV divided by N dot F. True. And then what do you have? The standard enthalpy of combustion plus the sum over all the products, the stoichiometric coefficient. Then the enthalpy at the temperature the product exits minus the enthalpy of standard 298 or 25 degrees C. That's at delta H. I just wanted to expand it, okay? Minus the sum of the reactants, the stoichiometric coefficient, then you have the enthalpy, the temperature of the incoming reactants minus the temperature of 298. Does all that make sense? Do you think I need the balanced reaction equation to go further? We need it. So give me the balanced reaction equation. All right? Go ahead and compute it for me. All right, so we know that the oxygen's the hard part. Let's write down the balanced reaction equation, CH3OH. And when you look at your fuel, maybe sometime you go like this. Watch out. Uh-oh, watch out, because a lot of students will forget that there is an oxygen in the fuel, because for most of our hydrocarbon fuels, there's no oxygen in the fuel. And then you'll go, okay, I'm going to get the oxygen from air, and we're going to produce carbon dioxide. A lot of times, the only place the carbon occurs is in the fuel, hence we can put the coefficient in front of the CO2 right away. What is that coefficient in front of the CO2? It is a 1. Then we look and we say the H2O. And at this point, often, there's no water in our air. It's dry air. There's only hydrogen coming with the fuel. We can balance and get the coefficient in front of the H2O. What is it? 2. Go slow here because oxygen is tricky. So we go right here. How many oxygens? 2. How many oxygens? 2. Add 2 plus 2? 4. I need to have 4 over here. I've got 1 right there. I need 3 from the air. See how I do the math in my own head? So this coefficient is 3/2. Tricky, isn't it? What's the number one wrong answer I get? They put a 2 there. They forgot that there's an O with the fuel. Got it? Now we have to balance it and finish it out with the nitrogen. So we're going to have N2, 3.76, and then we have the 3/2. Now, it's 100% theoretical error. If now they said it was 20% excess or something, I would modify it again. If you did modify it again, I encourage you to rewrite the whole equation and modify it then. Okay? But leave the 100% theoretical perfect amount balanced equation by itself. So, to continue with this problem, what is our enthalpy of combustion, standard enthalpy of combustion? Well, let's say I calculated that already, and it was negative 676,270 kilojoules per kilomole. We calculated for another fuel. I know you can do it correctly for methanol. In the interest of time, there's the answer for that part. But let's take a look at this sum over all the products, right? What we have to do is I'm going to bust that sum out. We have the number of moles of CO2, and then we have the enthalpy at 900 Kelvin minus the enthalpy at 298 Kelvin for the CO2. Makes sense? I need another parenthesis there. Plus the coefficient, stoichiometric coefficient in front of the H2O times, maybe I'll change the style of the bracket to make it more clear. Go like this, square bracket, okay. Square bracket, molar enthalpy at 900 Kelvin minus a molar enthalpy at 298 Kelvin, square bracket for the H2O. Plus the number moles of N2 times the enthalpy at 900 minus the enthalpy at 298 for the nitrogen. Did I do all the products good? Is that okay? Now the reactants. But take a look. What temperature do all the reactants come in? 25. So guess what this whole summation over all the reactants is? The inlet temperature is the same as the reference temperature. So we don't even need to do that. So that's good. Can I do this? What is this N for the CO2? 1. What's the N for the H2O? I left my O off. It's 2. And what is this N for the nitrogen? 5.64. How do I get these enthalpies? Go to the tables. So I'm going to click to the next page. So you go to this table A23 and you look for carbon dioxide and you look down the H bar as a function of temperature. The molar enthalpy at 298 is 9,364 and the molar enthalpy at 900 Kelvin 37,405. See where those two numbers come from? Likewise, you're going to need that for water vapor at enthalpy at 298, the enthalpy at 900 Kelvin. And then you're going to need it for the nitrogen, 298 and 900 Kelvin. Little tedious, but you got to be able to do it. Okay? So you substitute those values right there. And when you calculate it, what you'll find is that it's negative 50, I'm going to just say 2000 kilojoules per kilomole. It's negative 502,000 kilojoules per kilomole. That's how much heat will come out. The negative sign is indicating out of the control volume per kilomole of fuel that's going into the control volume and is completely combusted. There's no fuel in the products. Good? Adiabatic flame temperature. So certain fuels, when they burn hotter. That makes sense? Certain fuels, when they burn cooler. And if I want a really, really hot flame, guess what? Burn it with pure oxygen, not with the nitrogen tagging along. If I want a lower temperature flame, just get the oxygen from air. Maybe you've welded, maybe you've used a cutting torch, maybe you have some experience like this out there. You know different propane or MAP gas or acetylene burns at different temperatures. That's great. But now in this class, we can see it mathematically. So what we introduce is the adiabatic, no heat transfer, flame temperature. When you have no heat transfer away, that temperature of the products is the hottest it can be. So here is a little, I think this is a can of butane. And you have a little trigger and a little flame coming out. And we're going to get that temperature. When in the combustion, there's no heat transfer. It's adiabatic. You just have the air and the fuel, and boom, it comes out. Or the pure oxygen in the fuel, and you come out. Okay? So you would have an equation like this. What's Q dot when you want to calculate the adiabatic flame temperature? 0. What's W dot? 0. And the products, the enthalpy that it comes out at the adiabatic flame temperature, that maximum temperature minus the standard 298 that came in. So that's that delta H. And now for the reactants, typically they're coming in at room temperature. So this adiabatic flame temperature, often this whole group over here is 0 anyway. Often this group right here is 0. But now for the adiabatic flame temperature, you have that the sum of the stoichiometric coefficient times the change in the enthalpies over all the products is equal to the negative of the standard enthalpy of combustion. Now, what do you want to calculate? You want to calculate that term. Sometimes it's a sum of over 3 things. It could be the sum of, I have a carbon dioxide, a water, and a nitrogen. I have a sum of 3 things. So I have an unknown in this sum. It's tedious. You might write down in cap, bold. This is extremely tedious when you have to do it by hand. With a computer, it's easy. But what you have to do is guess T, the answer, and iterate. Guess and iterate, okay? So I'm out of time. We'll pick up there next time. Thank you for your attention.